We're looking at a paper called Rewarding the Rare, Uniqueness-Aware RL for Creative Problem Solving in LLMs by Ziwan Hu and a team from MIT, NUS, Yale, and NTU. It's tackling this problem in reinforcement learning called exploration collapse. So basically, algorithms like GRPO get really good at improving paths at one accuracy, but they do it by forcing the model to pick one single reasoning pattern, which just crushes diversity.
Exactly. And the core insight here is that we've been chasing the wrong kind of diversity. We've been measuring token level entropy. But the authors make this fantastic point that, solving a quadratic equation by factoring it versus using the formula, that's real strategic diversity, even if the token sequences look kind of similar to an RL algorithm.
So their solution is this uniqueness-aware RL. They bring in an LLM-based judge to actually cluster the different solutions, the rollouts, based on their high-level plan, not just the text. And if a solution is correct, but it's in a big cluster of the same old strategy, its reward gets pushed down. But if it's correct and it's in a tiny cluster, meaning it's a rare strategy, the gradient update gets a massive boost.
And the results really speak for themselves. They show huge improvements in the area under the curve for pass at K, so AUC at K, on really tough benchmarks. We're talking AMY, physics Olympiads, medical reasoning. It basically proves you can train for creativity without killing your accuracy.
Welcome back to AI Paper Podcasts. We are definitely getting technical today. This paper, it really gets to the heart of the scaling paradigm for reasoning models right now. If you're watching what's happening with models like DeepSeek R1 or Qwen thinking, you know that reinforcement learning is the engine.
It is the engine, but as this paper points out so well, that engine has a bad habit of getting stuck. It stalls out in these local minima. The term they use is exploration collapse.
Let's define that a bit for the engineers listening. It's not quite mode collapse like in GANs, but it feels related.
It's very related. So in the context of RLHF or RLAIIF, especially with something like group relative policy optimization or GRPO, the model is just trying to maximize reward. And usually that reward is pretty simple. Did I get the right answer? Yes or no. So once the model finds one reliable, low effort path to get that yes, it just exploits it ruthlessly.
And it stops looking for anything else. It stops exploring.
Completely stops. It just converges on that one safe reasoning pattern. And this is great for your pass at one score, right? The model is super consistent with its one trick, but it absolutely destroys the diversity of your rollouts. You lose that whole long tail of other, maybe more creative solutions.
And the paper's main argument is this happens because our whole proxy for diversity is just broken. We're looking at token level entropy.
Exactly. And this is really the key distinction to get your head around. High token entropy does not mean high cognitive diversity.
They have that great example in the paper with the quadratic equation.
Yes, let's walk through that. So imagine you ask a model to solve x squared to minus 5x plus 6 equals 0. Path A, it uses the quadratic formula, simplifies it all out step by step. Path B, it also uses the quadratic formula, but maybe simplifies it in one big jump.
Okay, so to a standard RL algorithm, those look different because the sequence of tokens isn't identical.
Right. High token entropy. The algorithm thinks, great, diversity, but the strategy...
It's exactly the same. It's the same algorithm.
Precisely. Now, contrast that with path C, factoring the equation into x2 by 3. Now, that is a fundamentally different strategic approach. But if the quadratic formula is just a little bit more common in the pre-training data, standard RL will just pour all its probability into paths A and B, and it will kill path C for being risky or weird.
So we end up with these models that look diverse on the surface. They vary their phrasing, but underneath they're cognitively rigid.
Brittle is the perfect word for it. And all the previous fixes, things like adding entropy bonuses or methods like forking tokens, they all fail because they operate at that surface token level. They can't tell the difference between just stylistic variation and actual strategic variation. Okay,
so let's get into their fix, Uniqueness-Aware RL. How do you actually implement strategy as a metric? That feels so abstract for a loss function.
It is abstract. So what they do is they use a proxy that can understand abstraction, another bigger LLM. The pipeline is really a clever tweak on the normal GRPO loop. Step 1 is just sampling. You generate K rollouts for a prompt, say K equals 16. Step 2, verification. Simple check, is it right or wrong? Your reward is 0 or 1. Step 3 is the new part, the judge.
And this is a much stronger model acting as a sort of critic.
Yep. If you're training a 7B model, you might pull in something like Qwen 72B to be the judge. The judge looks at all 16 of those rollouts, and it's prompted to cluster them based on their high-level solution plans.
And the prompt engineering must be critical here. They're telling the judge to ignore all the surface-level noise.
Absolutely. The prompt is something like ignore variable names, ignore how the algebra is rearranged, focus on the core idea. Is this a Newton's second law solution, or is this a conservation of energy solution? The judge just returns which cluster each solution belongs to.
Okay, so now we have our clusters. Let's say we have, 10 solutions in cluster A, the common one, and just one solution in cluster B, the rare one. How does that feed back into the gradient?
This is where they modify the advantage function. So they calculate a weight for each solution. Let's call it W. And W is simply 1 divided by the cluster size raised to the power of alpha.
Where alpha is just a hyperparameter, a knob you can turn to control how aggressive the reweighting is.
Exactly. So for those 10 solutions in cluster A, the cluster size is big. That makes the weight tiny. The model still gets a positive reward because it got the answer right, but the signal is really dampened. It's like a teacher saying, yeah, that's correct, but it's also really boring.
And for that lonely solution in cluster B?
Cluster size is 1, the weight stays high, so relative to all the others, its advantage is huge. The gradient update for that rare strategy gets a massive boost.
It's explicitly rewarding the correct and rare quadrant.
Precisely. And that could be a really dangerous game because rare can often mean hallucination, right? But because they gate it behind the correctness check first, they make sure they're only boosting valid, correct reasoning paths.
Okay, let's talk about performance, because my first thought is when you force diversity, you usually pay a price, a diversity tax on your accuracy. If you force the model to take the road less traveled, sometimes that road just leads off a cliff.
That's the standard intuition, yeah. But the data here really pushes back on that. They tested this on Quen 2.57b, Quen 3.8b, and Olmo 3.7b, and they ran it on these really hard benchmarks, math with AIM, physics with Olympiad Bench, and even medicine.
And they used AUC at K as the main metric. Why that instead of just looking at pass at 1 or pass at 10?
Because pass at 1 doesn't tell you anything about exploration. AUC, at K the area under the Turver pass, at K measures how much extra value you get from generating more samples. With the standard model that's suffering from collapse, generating 64 samples gives you almost no benefit over generating, say, 5. They're all the same failed or successful strategy. The curve just flattens out.
But with uniqueness RL,
the curve just keeps on climbing. On the AM benchmark with Quen 2.57b, the difference is just stark. As K goes up to 64, 128, even 256, the uniqueness model keeps finding new, correct answers that the baseline model literally cannot find, no matter how many times you sample it.
Which implies the model hasn't just learned one trick, it's learned a whole portfolio of strategies.
It has. And you can actually see this in the entropy dynamics. There's this great chart in the paper that tracks the policy entropy during training. With standard GRPO, the entropy just crashes. The model becomes deterministic fast. With uniqueness RL, the entropy stays high. In some of their runs, it actually goes up.
That's fascinating. So the model is holding on to its uncertainty or maybe its optionality deep into the training process?
It's like it learns that there's no single golden path. It learns that the problem space is wide, and it stays comfortable moving across that whole width.
I want to compare this to forking tokens for just a second, because that was sort of the state of the art for diversity before this, right? That method basically just tries to force the model to pick different words to start with.
Right. Forking tokens, or a similar idea called DAPO, they're very token-centric. They're basically saying, hey, don't start your answer with the word first again. But Uniqueness RL beat them pretty handily, especially on the humanities last exam and the physics benchmarks.
Which really proves that semantic diversity is what matters, not syntactic diversity.
100%. Manipulating tokens is just a heuristic. Manipulating strategy.
Yeah.
That's the real goal.
Okay, let's get into the qualitative stuff, the cover N analysis. This was my favorite part of the paper because it really connects the machine metrics to, human intuition.
Cover at N is a cool metric. It measures the model's recall of distinct canonical human solution methods. So if a textbook says there are 5 known ways to solve a problem, how many of those 5 does the model actually find?
And they looked at a geometry problem from AIM, problem 10, a triangle inscribed in a circle.
A classic. So the baseline model found 2 strategies, power of a point and Ptolemy's theorem. These are the standard tools you'd reach for. The baseline covered about 40% of the known human solution space.
And the uniqueness model.
It found all 5, 100% coverage. It found median similarity and a pure trigonometry approach.
Wow. So median similarity is not something you just, stumble upon by accident.
No, it's not. That requires knowing some pretty specific properties of this median point. It's an elegant but very specific geometric insight. It's probably very rare in the training data because it's harder or just less general than power of a point. Standard RL would suppress that path. Uniqueness-RL found it, saw it was rare, and cranked up its reward.
There was another example from combinatorics, right? The 2x2 grid coloring problem.
Yeah, the baseline just kind of brute forced it.
Yeah.
It turned it into a binary constraint formulation, just an algebra problem. The uniqueness model found a trail flow viewpoint. It actually visualized the problem as a flow of active edges through the grid.
That's a conceptual leap. That's not just solving, that's reframing the entire problem.
It is. It really shows the model moving from just calculating to actually reasoning. The visualization they have in Figure 4 shows it perfectly. The baseline solutions are all clumped together in the middle around the standard answer. The uniqueness solutions are fanned out, pushing towards the frontier of the solution space.
So this sounds incredible, but we all know there's no such thing as a free lunch. What's the cost? What's the catch here?
The catch is compute, specifically the judge. You are running an entire inference pass from a 72 billion parameter model for every single batch of your training data, just to calculate the rewards.
That is a massive overhead compared to just checking if output answer.
Oh, yeah. It slows down the training loop by a lot.
Sure.
You're fundamentally trading training speed for the final quality of the model. And there's another bottleneck. You're limited by how smart your judge is. If your judge is only a 7B model, it might not be clever enough to realize that median similarity is a genuinely unique strategy. It might just see it as noise and lump it in with something else.
So the student can never be smarter than the teacher's ability to grade nuance.
That's a great way to put it. And there's also the issue of local versus global rarity. The algorithm is only calculating rarity within the current batch, say the 16 samples it just generated. It has no memory of the entire training history.
So it might reward a strategy that's rare in this specific batch, even if the model has actually used it 1,000 times in previous batches.
Correct. It's a local pressure for diversity.
Yeah.
Now, to be fair, it seems like that local pressure is enough to push the global distribution outwards, but it's not a perfect system.
This feels like it goes way beyond just, passing tests on benchmarks.
Oh, absolutely. I mean, think about automated theorem proving or something like drug discovery. In those fields, finding the standard answer is useless. We already have that. We need the outlier. We need the chemical pathway that looks weird but actually works.
It's bridging that gap between pure optimization and something that looks a lot more like creativity. Usually RL is a narrowing process, right? It optimizes for the mean. This seems to make it an expanding process.
It's a lot closer to how we train elite scientists, I think. We don't just want a physicist who can churn through equations from a textbook. We want one who looks at a problem and sees a new connection, a new symmetry.
Which leads to a pretty wild implication. If we can train these models to explicitly go out and hunt for rare strategies,
we might start finding mathematical proofs or physics derivations that humans have simply missed.
Not because they're impossible for us to understand, but just because they are statistically so improbable in all of our existing textbooks and papers.
We're all limited by the human distribution of training data. This method pushes the model to the very edges of that distribution. And eventually, it's going to step outside of it.
And that's where genuine discovery happens.
Exactly. We're building an engine for novelty.
The paper is Rewarding the Rare. We've put the link to the ArcsFiv PDF and the GitHub repo in the show notes. The code's out there if you want to go and look at the clustering prompts yourself.
And the prompts for the judge are actually surprisingly simple, which is really encouraging. It suggests the whole method is pretty robust.
Thanks for listening to this episode of AI Paper Podcasts. If you're out there training reasoning models, you might want to take another look at your reward function.
Don't let your model be boring.
We'll catch you on the next one.